So, as Margarita said at the start of her talk, the impression was that I was supposed to be talking to a school for students, and so I prepared material that at least starts off by being rather easy, rather elementary. So if any of the senior professors have difficulty, I can slow down and say it more slowly. So the thing I'm talking about is basically geometry of varieties, meaning mostly projective varieties, versus the algebra of graded rings. So my point of view here is sort of basically the same as Professor Gurjar's yesterday afternoon. So graded means graded by n, so by positive integers, and finitely generated. So there's a way, there are ways between these two worlds, certainly not bijective or isomorphisms of category or anything, but nevertheless that are very useful given a variety to construct a ring and given a graded ring to construct a variety. So so if X is a projective variety and D is a suitable divisor, I can go to the ring R, X, and D. So this is, let me write it just once, the Riemann-Roch space of multiples of D. So I'm taking, so this is the set of all rational functions on the variety X with poles at most D. The Riemann-Roch space of LD. So, of course, this is the same thing as H naught of OX of ND. So, under really fairly general assumptions on D, but certainly not generally, this ring is finitely generated. So, a lot of the recent progress in dimensional geometry is saying that if D is, for example, the canonical divisor of an n-fold, of an n-dimensional variety of general type, then this ring is finitely generated. And many, many variants on that. It's, so on the other hand, the Hilbert 14th problem has counterexamples given by Zariski and many others in the 1950s. So this is not in general finitely generated, but it is in all the case I want, right? And then the converse is given Rxd, given a graded ring R. So this is just a general graded ring. I can go back to proj of R. And the proj of R comes equipped with this family of sheaves, OX of D, one for every D in Z. And under some circumstances, these two constructions are basically the same, are basically inverse, but certainly not in general, certainly not in any categorical sense. Yes? So, I'm a geometer. I want to construct varieties or do classification of varieties. Let me give a kind of example. I'm going to start with one or two examples, and then I'm going to come along to some kind of sort of serious grown-up theory. So, suppose I want to study curve C of genus 3. So a curve of genus 3 is a kind of abstract concept of mathematics, and maybe in the first instance we don't know that any such exists. But let's take on trust the Riemann-Roch theorem. So I'm going to take as my divisor D to be the canonical class of C. So, the question is, do there exist any curves C? Can we construct one of them? Can we construct a family of them? Can we construct all of them? Can we study their moduli? I want to write down R of C and KC. And so to do this, I need to use the Riemann-Roch theorem to tell me H naught of NKC. Right, so this is supposed to be a vector space. Vector space has a dimension. The first thing you need in this game is to know the dimension of these vector spaces. So at the moment I'm using Riemann-Roch and calculating them one at a time. Later on, these are given automatically as in bulk, in totality, by a single Hilbert series. And there are nice theories about the Hilbert series. So this is equal to 1 if n is 0, and 3 if n is 1. So that's the definition of the genus. The number of sections of KC is one definition of the genus, and then it's what is it? So the degree of KC is 2g minus 2 is 4, and so this is 1 minus g plus 4 times n. So this is 4n minus 2 for n greater than or equal to 2. So if we're studying a ring, then I write down H naught of x of KC, and this is three-dimensional, so I choose a basis, x1, x2, x3. So when I look at H naught of x of 2kc, we know for sure that this is six-dimensional, and so we might write down y1 up to y6 as a new basis. However, we already own some elements in here. Namely, if I take x1 and x2, so if I take x1 in O of kc, and some other x2 in O of kc, then the product x1, x2, this is just using the product of these two line bundles. If I multiply a function with given poles by another function with given poles, I have a product function with the sum of the two given poles. So here we own for sure x1 squared, x1, x2, x2 squared. Let me stop writing this. S2 of x1, x3. So there are 6 monomials there. Yes? So counting those monomials here, you can do it one at a time. Everybody knows there are 6 quadrics in 3 variables. On the other hand, if you use the Hilbert series, you don't have to do this calculation at all. This is just handled automatically. Right? So there are 6 elements here. So I've got a 6-dimensional vector space and 6 elements, so bingo, I must have a basis. Right? And so it turns out, continuing this calculation, and you can do the calculation for yourself as an exercise, and it's a valuable exercise. So you're not allowed to use geometry. You have your hands tied behind your back. You're only allowed to use this ring calculation. You see that either these 6 are linearly independent, and in that case, the ring of C and KC is K of x1, x2, x3 divided by F4, right, divided by a quartic equation. So if you continue this calculation, you'll find there are 10 of these monomials in degree 3, and there are 15 of these monomials in degree 4, whereas the Riemann-Roch space is only 14-dimensional. So there must be a relation here. And if you do this calculation, honestly and in good faith, you will come to the conclusion that given that these 6 are linearly independent, this is the only possible structure for the ring. Or, so there's one linear dependence relation, meaning that C maps to some conic in P2, right? The x1, x2, x3 here are linearly independent when you restrict them to C. That means there's a curve given by a quadratic equation in P2, and C is the image of that. And then, in this case, R of C and KC is K of x1, x2, x3. Y, if these 6 are not a basis, if they're not linearly independent, then I've got to add at least one more element to make them a basis. And this is the new element I'm putting in to compensate for this equation there. And then divide it out by 2 equations. So now 2 equations are Q, which is the equation of this relation here, and then a new relation saying that y squared equals F4. Yes. So what have we gained by doing this? So you may notice that these 2 constructions can be put together as a single construction. Namely, I can write C2, 4 in weighted projective space 1, 1, 1, 2. So this is weighted projective space. Yes, given by these 2 equations. So it could be given by, for example, lambda y plus q equals 0 and f4 of, so this is x1, x2, x3. This could be f4 of x1, x2, x3 equals 0. Sorry. So if y squared equals that, then I can take the q, I can substitute y. If lambda's 0, then I've got this model. If lambda's not 0, I can just get rid of the y and just eliminate the y from the equations. Yes? So this tells us how to construct every curve of genus 3, and it also tells us how to mediate between the hyperelliptic guys and the non-hyperelliptic guys. So, everybody, I'm sure everybody here has done this exercise using geometry, using coherent cohomology and ampleness criteria and so on, but it's also an exercise in these rings. So another exercise is if I have a surface S of general type. So general type, I'm just going to assume means KS ample. So, there are lots of specialists here who know everything about -2 curves and how to contract them to Duval singularities and that kind of thing, and so on. What I say here, this is not the definition of general type. This is a popularized, a kind of downgraded version of it. But it works perfectly well, and it just takes a lot less time to explain. So let me just assume that general type means KS ample. So if I take PG equals 4, K squared equals 5, then geometrically speaking, you write phi from S maps to P3, and you say, well, if we're lucky, the K will be a free linear system, no fixed components, no base points, right? And in that case, just by degree correspondence, this S must be phi K must be an isomorphism, and we get that the graded ring of C and K of S and KS is x1 up to x4 divided by a relation F5. So this just says the surface is S5 in P3. Yes? And so in this case, you can also ask what happens if this is not a free system, and I'll explain that next time, and it's much more complicated than this. But in spirit, it's sort of similar to this. It's a complicated construction, and I'll explain that tomorrow as a kind of prime example of when this method of unprojection works. Okay, so that's the first elementary thing I wanted to say. So I want to talk about Gorenstein rings. So as an excuse for not giving you any proper definition, I want to say there are 4 or 5 completely different, superficially completely different definitions. This is not an elementary idea. This is a complicated idea, and so there are 4 or 5 quite different definitions of what a Gorenstein ring is, and to go between any one of them is a whole chapter in a commutative algebra textbook. So the rings that I construct in this way are usually Gorenstein, and so I should say this ring here, I'm talking about proj of the ring, but I can also take spec of the ring, and then I get this picture, which is the same as the picture that Professor Gurjar had, which is this is an affine variety with a given origin. This is an affine variety with a C star action. Let me say I'm working over K equals C. So if there's anybody in the audience who's smart enough to think about it, you can try and do it over an arbitrary base scheme. And most of what I say works over an arbitrary base scheme, but not all of it, right? Anyway, C star is much easier to describe. So there's an orbit here, right? And so when I construct weighted projective space like this, I'm thinking of variables of degree 1, 1, 1, 2, and I have, in that case, these orbits of C star are literally parabolas, except for some which are entirely in this 1, 1, 1, 1 place. Yes? And the ring I'm really concerned with is the local ring at the origin. So there are 2 rings that you can work with here. There's the homogeneous coordinate ring, which is this construction, or there's the local ring at the origin. So Grothendieck's-Lefschetz principle says that one of them is, says that these 2 rings determine each other. So the local ring at the origin, together with its C star action, completely determines the graded ring. So I'm assuming that the C star action is fixed. So that's the principal difficulty that Professor Gurjar was facing yesterday. That he was considering isomorphisms of graded rings, possibly not preserving the grading. Okay, so let me say for a local ring. And when I'm doing a projective variety, the local ring I have in mind is the local ring at the origin there, right? So for a local ring, a Gorenstein always means Noetherian. It doesn't make sense in commutative algebra to talk about Noetherian if you don't have about Gorenstein if you don't have Noetherian. So it means Noetherian, and it also means that a fixed dimension. Yes, so we're talking about Gorenstein is sort of like the condition to have a manifold, and you can't say manifold without saying n-dimensional manifold. You must have a fixed dimension. So local, if I've got a local ring A, M, then one of the definitions of Gorenstein is that there exists a regular sequence of length n. So this means I can choose maybe y1, y2 up to yn in M, with the property that y1 is a non-zero divisor, and then that y2 is a non-zero divisor modulo y1, right, and so on and so on, right? Regular sequence of length n is the dimension of A. So then when I do A divided by x1 up to xn, divided by the ideal generated by x1 up to xn, this is Artinian. Zero-dimensional, local, and Noetherian. So, look, I told you I'm a geometer. And when you see a high-dimensional thing, the thing you want to do is take a hyperplane section. So then I just get a variety of one dimension fewer, right? And the problem with this is that it might happen that I think I'm doing the right thing by taking a geometric section of it, but it might happen that when I do the algebraic quotient, that I have some kind of little piece of nilpotent fluff sticking up out of the origin. This genuinely happens. There are counterexamples. If somebody hasn't seen it and wants to ask me about it afterwards, I can certainly give a counterexample. Yes? And so here, this existence of the regular sequence means that I can act like a geometer, take a hyperplane section, and then take a hyperplane section again until I get something zero-dimensional. Yes? Yeah, I do. Thank you. Yes? And then, so if dimension A is 0, then Gorenstein means that the socle of A is one-dimensional. Right. So this. Let me draw a picture. Here's my picture of A. I'm thinking of this A as having a monomial basis. So it's basis. This is Artinian, means finite dimensional. So I have a basis of it made of monomials. And when I do multiplication by the maximal ideal, I'm shifting everybody up one step. Yes? The socle is Hom. So this is Hom over A of A mod M into A. So this is the residue field, K. And I'm asking for all the guys in the ring where multiplying by the whole of the maximal ideal is 0. So this is, I want this to only have a single basis element. So the consequence of this is that Hom A K over K is isomorphic to A as K alpha, a K module, as an A module. Yes? And so it means that this picture is its own dual. It means you can take this picture and flip it like that by doing this Hom A K. This works even if you're not defined over a field. This works for general Artinian rings, right? But you have to be just a little bit careful about these things. Yes? So I'm going to use two other. So I gave you a definition, but the definition is sort of basically useless. So the Gorenstein is the condition that I can cut it by hyperplane sections, and at the end of it I get this nice self-symmetric picture. Yes? So let me say codimension. So codimension means the minimum number of generators of A minus the dimension. Right. So when I was doing one of these rings, for example, then I'm writing down 4 generators, and this is the cone over, and this is the affine cone over a projective curve, and so this is 2-dimensional. So this is 2-dimensional, and I need 4 generators for the ring, so this is codimension 2. Yes? So you know, when I say the variety XD has codimension something, I'm talking about the minimum number of generators needed for this ring. Yes? So, you know, you have a kind of sequence of results that says everything is very, very simple at the start. So codimension 1 means that, so Gorenstein means that V a hypersurface. Codimension 2, so in this case Gorenstein is equivalent to Cohn-Macaulay. Gorenstein, if and only if codimension 2, complete intersection. So, you know, there was an example already on the board here. This is a theorem, this is called the Hilbert-Birch theorem. Codimension 3 already starts hotting up. Right, so Gorenstein, if and only if, the ideal of R, so R, it means that R is K of some generators, x1 up to xn, divided by some ideal. So this ideal is the 2k by 2k Pfaffians of a skew 2k plus 1 by 2k plus 1 matrix. Yeah. So you might have thought I have a hypersurface here and have codimension 2 complete intersection. So the natural thing to continue that might be codimension 3 complete intersection. So codimension 3 complete intersection might be something like F3 minus F2, F1, 0, 0, skew symmetric. Right? And that means that the Pfaffians in this case, this is 3 by 3, so the Pfaffians are something like the square root of the determinant of blocks like this, and so the codimension 3 ideals are contained, codimension 3 complete intersection are particular cases of this with k equals 1. Right? However, they almost never happen in real-life combat. Right? And so the one that happens all the time is the 4 by 4 Pfaffians of 5 by 5. So I know several hundred naturally occurring varieties that require this structure. I know maybe 1 or 2 or 3 varieties that need either 3 by 3 or 7 by 7. So in practice, this is the case that we have to master. Anyway, the point is that I write down, if I write down this matrix, this is the matrix of first syzygies. So this matrix is the first syzygies. This is called Hilbert-Birch. This is called Buchsbaum-Eisenbud. So, you know, there's a kind of moral here, which is the first syzyges already know the relations. So first, you know, I've got a matrix here which is skew, then for 1 up to for 2k plus 1 is the kernel of this matrix. Yes, that's just Cramer's rule. It's just the skew-symmetric version of Cramer's rule. So in other words, the matrix of syzyges tells you immediately what the Pfaffians are. So the Pfaffians are the equations. The matrix here might have linear entries or very, very simple entries in the generators of the ring, whereas the Pfaffians are already, you know, for example, quadratic or cubic polynomials in those entries. So the equations are much simpler than the syzyges. So the syzyges know more about the structure than the equations do. Right? This is a principle. And so codimension 4, we don't know. Yes? So there are practical methods that give many results, but definitely don't cover every variety. And there's a theoretical structure theorem that I don't really have time to go into, based on this principle that the first syzyges know more about the structure than the variety itself. That's in this published paper. It's been a preprint for about 10 years. Eventually published paper. And this is mostly what I'm talking about. But unprojection is something, which I'm coming to in a minute, is a method of going, codimension C up to C plus 1. So unprojection, it's a certain inverse of projection. Yeah? How much time have I? Okay. So let me give some more simple examples that everybody already knows. So if I take S3 in P3, a cubic hypersurface, and let's suppose it contains a line, right? Then it means that S3, so the line might be given by x1 equals x2 equals 0, right? And then S3 might have equation, for example, minus a times x2 plus b times x1. Yes? So the equation of S has to be in the ideal generated by the ideal of L, so it has to be a multiple of x1 plus multiple of x2. So when you see this, you may immediately think to write down S equals a over x1 equals b over x2. Yes? So, you know, I've got this projective space has coordinates x1, x2, x3, x4. Because I said cubic, these a and b are quadratic in the x's. And so this guy is naturally, so what is this guy? So you can think we're working on the affine variety, in which case it's just what it is. It's a rational function on the affine variety. But it's naturally homogeneous of degree 1. So it's a form of degree 1, a rational form of degree 1 with pole on L. Yes? So if I now move to P4 with coordinates x1 up to x4 and S inside there, I can write down the equation S times x1 equals A, S times x2 equals B. Yes, okay. And I have a codimension 2 complete intersection here, and a preferred point, so there's PS, which is 0, 0, 0, 0, 1, the point where S is non-zero and everybody else is 0, right? And there's a, so this is a new variety. Let me write T, for example, and there's a birational map there that is, the linear projection from the point P. Yes. Now, everybody has seen this, and everybody thinks I'm talking about non-singular Delpezzo surfaces. So if S3 is non-singular along the line L, it means that A and B have no common factors, and then the map from S3 to T is a morphism. It's the thing given by Castellanova's contractibility criterion. Contracts a -1 curve to a non-singular point. However, the equations make perfectly good sense without that assumption. The A and B can be arbitrary, really arbitrary things, as long as x1 and x2 are a regular sequence, and this -8x2 plus bx1 is also a regular element. So this is about a projectively Gorenstein variety containing another projectively Gorenstein variety as a divisor. And that's the context of this unprojection theorem that I'm going to talk about. Yes? There's another point. This PS is, by construction, this is a non-singular point. Right? Because I have the unprojection ideal here was generated by x1 and x2. These are two of the coordinates, and so I have two. When I set S equals 1 here, I have two equations with linearly independent Jacobian matrix in x1 and x2. Right, so the derivatives of this, so x1 and x2, it's guaranteed that x1 and x2 can be written as implicit functions of the other variables. So this isn't, I get a non-singular point. So, I don't have time to draw the picture again separately, but if we were thinking of this as an affine equation, what I've done is I've got this S here, and I'm just taking S as a new variable. So that sends the line L to a point at infinity, which is not in the affine variety at all, right? And it's just the graph of taking the graph of S. So in this case, in affine terms. Yes, and so if T contains in its turn a line L, let me call it a different name. So now I have T is Q1 intersect Q2 in P4, and let me just ignore the old coordinates. These are x1 up to x5. Suppose that I've got a line M in there. Yes? So then M is x1, x2, x3. So it's a codimension 3 complete intersection. And the Q1 is, for example, A x1 plus B x2 plus C x3. So now I don't know how to do this trick here to make this come out in the right order. Q2 is maybe, I don't know, let's just continue in the alphabet. X1 plus E x2 plus F x3. So, you know, Castelnuovo's contractibility criterion says that I can take this line M and contract him to a point, a non-singular point, right? So, you know, I want to, and you know, if you know the proof of it, you know that you have to write down a form that has a pole along M, right? And I'd like to do this in straight projective space with all degrees 1. And so how am I going to do that? So let's take these equations here and write them in the form A, B, C, D, E, F times x1, x2, x3 equals 0. Yeah? Completely harmless rewriting of the equations. Yes? However, now I have 3 independent variables and 2 linear equations between them. And we know how to solve that. So Cramer's rule says there exists a constant of proportionality So that's just to remind you this is stuff you did at school, right? So that I've got S x1 equals BF minus EC, or S x1, x2, x3 equals wedge 2 of this matrix. Yes? And so I've got 2 equations here. These are this is a codimension 2 complete intersection. That contains a codimension 3 complete intersection. And so I've got 2 equations here, and then I've got 3 new equations here. Right? And we can manipulate these to put these in the form A, B, C, D, E, F, S, x3 minus x2, x1, and then Pfaffian of this. 4 by 4 Pfaffians of this equals 0. So let me, 4 by 4 Pfaffians, we're going to need this again. I'm sure that most of you have already seen this. If I've got a matrix M skew, and I've got IJKL, then Pfaffian IJKL is MIJ times MKL minus MIK MJL plus MIL MJK. Yeah? So this is exactly like the definition of determinant that you give in first year linear algebra. Right? It is an alternating, a sum over the symmetric group. In this case, symmetric group on 4 elements, and each element would appear here 8 times if I allowed the repetition. And if you just get rid of the repetition, this is what you get. And this is, you know, by construction, it's the square root of the determinant of this guy. Yeah. So let me just write down some of this. Instead of talking about the theory, let's see what it says. It says that S times x3 minus A times E plus B times D equals 0. Right? And so S times x1, S times x2, X times x3 appear in exactly the same way. Yes? And then the equations not involving S are the Pfaffians like that. So one of these Pfaffians is D times x1 plus E times x2 plus F times x3 equals 0. Right? So these 5 equations here that are the 2 original equations and the 3 unprojection equations, the three equations involving this unprojection variable are given by this 5 by 5 matrix. So this is an illustration of Buchsbaum-Eisenbud. So of course everybody knows this. The Delpezzo surface of degree 5 is intersection of with Grassmannian 2,5. Yes? So let me talk about the unprojection theorem. So this is Kustin and Miller. I think it's 1983. I've got it written down. I usually get it wrong, but anyway, approximately 1983. And Papadakis and Reid, 2004. So the theorem says this. So let me state it first. Local. There's a local version and then there's a projective version. So suppose I've got D in X, both Gorenstein and codimension 1. So these are affine. Yes. Then I can write down. I want to write down, and there is a preferred class of elements S, so that when I do, S can be viewed as, so let me explain. I've got omega X is locally free, and so is isomorphic to OX. And omega D also is isomorphic to OX, OD. Right? So these are assumptions. The thing I'm writing down here are the Serre-Grothendieck dualizing sheets, dualizing modules if you prefer, if you want to be purely algebra. Yes? And so, you know, I can explain that a little bit, but it takes time and so on, and it's probably better if I explain that after the talk. Yes? So it can be viewed as a homomorphism S from ID into omega X, so that its Poincaré residue generates, is a basis omega D. Yes? So I can also, so this thing here is OX. It's isomorphic to OX. So if you know, at some point I have to choose an isomorphism. That's like choosing an orientation on an orientable manifold. So here I've got omega X is, I've got this thing. So in other words, this is a rational form with poles on D. And this condition, its Poincaré residue basis omega D, which I'm just going to explain, says that it has rational forms with poles exactly D. So in other words, this guy is a basis for all rational forms with poles on D. All rational forms with poles on D can be written as regular forms plus a multiple of this S. Yes? And then when I do OX of S, so this is going to be called OY, so I'm sorry, it should be called RY. Right? This is OS of X, so this is, I'm sorry, I want to write down FSFI equals GI. Let me explain this. Is again Gorenstein. Okay, so let me come back and explain the terms here. I won't say what the projective version is because you know, probably for most of you the projective version is sort of intuitive, whereas the local version is a lot of gobbledygook in commutative algebra. Yeah. So the projective version is D in X in some weighted projective space I'm assuming they're both projectively Gorenstein. So as I explained, the definition of this is that if I take their homogeneous coordinate rings and I take the zero, the maximal ideal in that, the irrelevant ideal, the 0 point, take the localization of that, these are Gorenstein rings. Codimension 1 and omega x equals OX of KX. So this weighted projective space has on it these O of D for all D and Z. Right. So if I can take these guys and restrict them to X, and I get this sheaf. So projectively Gorenstein implies in particular that omega X is a multiple of the is one of the structure sheets. It's one of the graded structure sheets. Omega D is OX of KD, and KX is greater than KD. Right. Then let me first explain that little assumption here. So in this case, well, where have I got these del Pezzo surfaces? So this KS here, KS3 is O of minus 1, and K of L is OL of minus 2. Right? So this assumption here is this minus 1 is greater than this minus 2. Right? So then there exists an S which is in HOM of ID O of KX minus D. Right? So I can think of this as a rational form with poles along D. Right? And when I do, if I do Y inside weighted projective space adjoined S. So, I don't want to introduce all the notation here. This one is x1 up to xn, this one is x1 up to xn and S. And the x's had their weighted degrees there, and here the S has this weighted degree kx minus kd, is again projectively Gorenstein. Right. So it's the same theorem, assuming it's for people who already know what the Grothendieck-Lefschetz principle is, it's just the same theorem. Here I have a local thing, which I can think of as locally at the base of the affine cone, and here I have the projective thing, which is just an interpretation of the local result. Okay. So let me just explain all that omega stuff going on. Grothendieck-Serre duality in this context says that omega D is x1 of O D omega x, and then here with OX. So, you should really think of this as being very close to the definition of the dualizing sheaf, right? We're assuming here that X is projectively Gorenstein, so X has a nice dualizing sheaf here. This omega X here has a dualizing property for the category of all sheaves on X. So the category of all sheaves on D is a subcategory of the category of sheaves on omega X, namely it's the ones killed by the ideal ID. Yes? And so, this is the thing I'm writing down. It looks sort of very fierce, but if you know, you can learn duality theory very easily. And this is just a tautology. This is just the part of the definition of the dualizing sheaf. Yes. And so, what on earth is this? So, let me write down sort of very, very conventional sequence. D is a subsheaf of D is a subscheme of X with ideal sheaf ID. Yes? So I take this sequence and I do hom star omega X over OX. Yes? And the thing I get is 0 goes to omega X, goes to omega X of D, goes to X1. The thing this is omega D, the thing I've written down here. Yes, goes to 0. So, you know, probably most of you have in mind the case where X is a normal variety and D is a Weil divisor on it. Right? So in that case, omega X is something to do with differential forms, top degree differential forms, and these are top degree differential forms with pole along D, yes, and they're mapping down here with Poincaré residue. So omega X of D is hom ID, curly hom ID omega X. It's just a definition. I'm allowing poles on D. That's an interpretation in the normal variety case. And this has a Poincaré residue down to omega D. Right. So, you know, this is just the adjunction formula. So especially people who've learned algebraic geometry via Griffiths and Harris think that duality theory is something to do with differential forms. And I think that's just nonsense. Duality theory is to do with hom. And we're seeing hom here in action. So I hommed this sequence into omega X. The omega X has this perfect duality for sheaves on X. And I get, as a result, a perfect duality for sheaves on D with coefficients in this omega D. Yes? And this is, so let me make a point here which you might find slightly shocking. I said here Gorenstein in codimension 1. There are no other assumptions. These can be arbitrary schemes. These can be as reduced, as non-reduced, as singular as they like. The D can sit entirely in the singular locus of X, so it is not a Weil divisor. This is a very, very general result. And the power of the result comes from taking Grothendieck duality as it's stated and not trying to interpret it in terms of differentials. Yes. So I had in mind to give one or two examples of constructions that you can do using this theorem, and you can't do without it. So let me just give one kind of quite pretty little example that was worked out by, my former student Stavros Papadakis has about 20 papers with unprojection in their titles. So if you want to know more about it, you can read my different papers, look at the papers I refer to on my website here, or just Google Papadakis and you'll find this. So this result I want to talk about is Georges Neves and Stavros Papadakis. So suppose that we want to construct a surface with, I want a surface of general type. So let's just say straight away KS is ample and Q equals 0. And I want that PG equals 5, K squared equals 12. Right. So, I take, geometrically speaking, I take my surface S and I map it. Let's assume, I can assume also that Kx is free. I'm just, at the moment, just trying to construct one such surface. I don't yet know that such a surface exists. I'm trying to construct at least one such surface. Right, so this probably maps to S bar in P4, and this probably has three nodes, virtually non-existent double points, as the Italians used to say. So three of these points where two surfaces cross absolutely transversally, crossing one point. The image is not Kern-Macaulay, and so on. So how to make S? How to make any single example of S? And so what they do is say this. They say, let's start off from X4, hypersurface of degree 4, contained in P7, and the P7 has coordinates xi and yi. I equals 1 to 4. Yes? And suppose that X4 is in the product of the ideals xi, yi. Yeah? So I have a quartic. I have some kind of quartic hypersurface. So this is X4. And it contains inside it four codimension 2 linear subspaces. Right? So all of this is taking place in some ambient space. We don't really care about the ambient space, but let's, to be correct, let's write it. Yes, and these four guys here, these 8 guys, because we're in P7, they form a regular. The sequence of length 8 is a regular sequence for the P7. Yes. And so, question? So because of this xi, yi, I can write, for any I can write equation of x4 is xi times, so let me continue the little game I was doing before, bi minus yi times ai, minus plus equals 0. Right? And so this says introduce zi, which is exactly the formula I had before, a over xi, ai over xi plus equals bi over yi. Yes? And I do this 4 times. And what I get is x bar contained in P. So it's P 1 to the 8th, that's the original variables, and then 2 to the 4th. That's these 4 ZIs. Yes? So the theorem says I can do this. There's not any kind of doubt about this. I have there's a published theorem that says that this works. Yes? So on the other hand, you can also use this. You can also write the equation Zij equals something appropriate. Right? And the reason we know that you can do this is because if I introduce Z1 and Z2, I'm now Gorenstein codimension 3, and so I have basically a game like this of Pfaffians. So this is from 5 by 5 Pfaffians. So let me just be clear about this. If I introduce Z1, it means I now have a codimension. This was a hypersurface. If I introduce one more variable, I have a complete intersection in codimension 2. Right? And then if I introduce a second Z2, it means I'm going to have something codimension 3 in P9 with these 2 new variables. And I know 4 of the equations. So it must have oddly many equations by this Hilbert-Birch theorem, by this Buchsbaum-Eisenbrod theorem. And so you mess around a bit and you find out how to write these 4 equations as 4 of the Pfaffians of a 5 by 5 matrix, and that gives you the 5th equation. Right? And so this is defined by 8 equations in degree so it's given by these 8 equations, xi times zi, and they're in degree, z's got in degree 3, and 6 equations in degree 4. Yes, and now, so I want now just to treat this thing, I want to think of this as being some kind of universal 4 times parallel unprojection. So I have this variety here that has 4 independently pre-existing planes in it, codimension 2 linear subspaces, and I can unproject each of them. And the unprojections are independent things. So this is a parallel process. I can introduce these zi's in any order I like, right? So I want to think of this x bar here as being a key variety for these constructions. So if I do x bar intersect what do I want to do? I want to intersect by a quadric and 4 HIs. Right. This is so I had an x. This is 6-dimensional. So 6-dimensional sitting in here. He's codimension 5. I want to cut him down to this sitting inside P4 and codimension 2. So right, and so here I have to write down so these 6 equations in degree 4 say Zi, Zj equals something, right? And that means that this variety here has 4 points that are 1/2 of 1, 1, 1, 1. It's a 6-fold, so these are 6 of these guys. Yes? So I already explained how to do this. The Zi satisfies these 2 equations, xi times zi and yi times zi equals 0. So his local tangent space is generated by 6 orbinates, right? And then I have to take account of the fact that the z has degree 2 here, and I get this half of 1, 1, 1, 6. So this variety here has 4. So there are 4 points like this, 1 for each eye. Right? And so what I'm going to do with this x bar is I'm going to intersect by a quadric. So a single quadric gets rid of all of that stuff, right? And then intersect with 3 hyperplanes H, right? And this is my S. So the S is constructed in his canonical model as a pullback, actually just as a intersection of this key variety. Yes? So I had another very pretty example to do, but I don't have time to do it. Tomorrow I have sort of slightly more serious applications. So the reason for Nevsky and Papadakis for doing this is they can take this S and they can divide it out by Z0. Yeah, and this is Campanelli with Z6. Anyway, that's you know. So this is the thing I'm talking about is a very pleasant game to play. It certainly doesn't solve all the problems in the subject. Okay, let me leave it at that. So as I said, I have one copy of these lecture notes to give away to any deserving students, or any professor who knows deserving students.